Hey everyone, all right, let's dive into a topic that is, I guarantee you, gonna be on your Class 10 physics exam. We're talking about electric circuits, specifically the big showdown, series versus parallel. Let's get right into it.
So, have you ever stopped to think about this? Look around you. Your TV's on, your computer's running, the lights are working, but what happens if you unplug your phone charger? Nothing, right? Everything else just keeps on going. Why is that? In other words, why on earth are household appliances never connected in series? That's not just a random fact, it's pure physics, and by the end of this, you're going to know exactly why. This is our big mystery for today.
Okay, here's how we're going to break it all down. First, we'll cover the basics of circuits and our big question. Then, we'll look at the flaw in series circuits. After that, we'll see how parallel circuits come to the rescue. We'll crunch some numbers, do a final showdown between the two, and wrap up with a checklist to make sure you're totally exam ready.
All right, Section 1, circuits and the big question. So first things first, what exactly is an electric circuit anyway? Let's make sure we've got the fundamentals down.
Okay, so an electric circuit is basically a closed path for electrons to flow, which is what creates current. The key word here is closed. Think of it like a racetrack. If the track is complete, the cars, our electrons, can just keep going around and around. But if there's a break in the track, everything screeches to a halt. A switch is basically just a drawbridge on that racetrack. When you flip it off, the bridge is up, the path is open, and nothing flows. Flip it on, the bridge is down, the path is closed, and boom, you've got current.
All right, moving on to Section 2, the series circuit flaw. So, could this be the answer for our homes? Let's dig in and see.
So, what makes a series circuit a series circuit? It's simple. There's only one single path for the current to flow. That's it. Imagine a one-lane country road. Every single electron has to follow that exact same path, one after the other. It has to go through the first light bulb, then the second, then the third. There are absolutely no turnoffs or shortcuts.
Okay, exam alert. You'll probably need to know how to derive this formula, so let's walk through it. It's actually pretty logical. Step 1. The main principle for series is that the total voltage from the battery gets shared or divided among all the components. So V equals V1 plus V2 plus V3. Simple enough. Step 2. Now we bring in our best friend, Ohm's law, which says V equals IR. We can rewrite the voltage for each resistor using this. So V1 becomes IR1, V2 becomes IR2, and so on. Step 3. We substitute that back into our first equation. So now we have IR equivalent equals IR1 plus IR2. You see where this is going? And for the final step, remember that one-lane road? Well, because there's only one path, the current, I, is the same everywhere. It's a constant, so we can just cancel it out from both sides of the equation.
And what are we left with? This nice clean formula. Rec equals R1 plus R2 plus R3. All this means is that to find the total resistance in a series circuit, you just add them all up. That's it. Super easy to remember for the exam. Okay, so let's get the final verdict on series circuits. The current is the same everywhere. The voltage gets split up, and importantly, the total resistance just gets bigger and bigger with every new thing you add. But here it is, the fatal flaw, the real deal breaker. If one component breaks, say one light bulb in a chain burns out, the whole circuit goes dead. Poof, everything turns off. Why? Because that single path is now broken. It's an open circuit. And that right there is the answer to why your house isn't wired this way. Imagine your fridge turning off because a lamp burned out. No way.
So, Section 3 is the parallel circuit solution. Since series is a no-go, let's check out the alternative.
Now this is a whole different ballgame. In a parallel circuit, the current actually divides. It flows through multiple separate paths, or what we call branches. So if a series circuit is a one-lane road, a parallel circuit is like a massive highway with multiple lanes. The current flows out of the battery, gets to a junction, and splits up. Some electrons take one lane, some take another, and they all meet up again on the other side.
And just like before, we need to know the derivation. It's kind of the reverse of the series one. Step 1, this time it's the current that gets divided. So the total current, I, is the sum of the currents in each branch, I1 plus I2 plus I3. Step 2, we use Ohm's law again, but this time we'll arrange it as I equals V over R. Step 3, we substitute that into our main equation. So we get V over Req equals V over R1 plus V over R2, and so on. And here's the most important part for parallel circuits, step 4, because each branch, Each lane on our highway is connected directly across the battery. The voltage V is the same for every single branch. It doesn't get divided. And since it's the same everywhere, we can just cancel it out.
And this leaves us with this, admittedly slightly stranger-looking formula. 1 over Req equals 1 over R1 plus 1 over R2, and so on. So the inverse, or reciprocal, of the total resistance is the sum of the inverses of all the individual ones. It looks a little weird, but the logic we just went through is solid.
So let's wrap our heads around the parallel circuit. The voltage is the same across everything. The current gets split up. And here's the really cool part. The total resistance actually decreases the more stuff you add. Think about it. More lanes on a highway means less traffic jam, right? It's easier for the cars to flow. Same idea here. And this brings us to the big advantage, the whole reason we're here. If one component breaks, say your lamp fizzles out, that lane is closed. But who cares? The other branches, the other lanes for your TV and computer are still wide open. The current just keeps flowing through them. And that is the solution. That's why your house is wired in parallel.
Okay, theory's down. Let's move to section 4, putting formulas to work. Time to solve a couple of classic exam problems, step by step, so you know exactly what to do. First up, a series circuit problem. We've got 3 resistors, 10, 20, and 30 ohms. How do we find the total resistance? It's super straightforward. Step 1, you write down the formula. Req equals R1 plus R2 plus R3. Step 2, you plug in the numbers. Req equals 10 plus 20 plus 30. Step 3, you do the math. The answer is 60. And please don't forget the units. It's 60 ohms.
Okay, now for the parallel circuit, using those exact same resistors. Step 1 is to write down the right formula. 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3. Step 2, we substitute our values. So that's 1 over 10 plus 1 over 20 plus 1 over 30. A little fraction math gives us 11 over 60. Now stop, red alert. This is the #1 mistake people make. Your answer is not 11 over 60. That's 1 over Req. For the final answer, you have to flip it upside down. So Req is actually 60 divided by 11, which comes out to about 5.5 ohms.
All right, section 5, series versus parallel, the showdown. Let's put everything we've learned into one simple comparison. This is your ultimate revision slide, so pay close attention.
Let's break this down. For current, in series, it's the same everywhere. In parallel, it divides. For voltage, in series, it divides. In parallel, it's the same. You see how they're opposites? Now, equivalent resistance. In series, it just gets bigger and bigger, but in parallel, it gets smaller. Finally, practical use. Series circuits are for simple stuff, like decorative fairy lights, but for the important things, like your entire house, it's parallel all the way.
And finally, Section 6, your exam-ready checklist. We're almost there. These are the key takeaways and tips to make sure you score full marks on this.
Okay, lock these 4 points in your brain. First, equivalent resistance is just a fancy term for the total single resistance that could replace the whole group. Second, here's a pro tip for checking your math on parallel circuits. The final answer for Req will always be smaller than your smallest individual resistor. Remember our problem? Our smallest was 10 ohms, and our answer was 5.5, so we're good. Third, here's a great concept question they might ask. Why does a thick wire have low resistance? Well, it's like having a ton of thin wires all in parallel. More paths for the current to flow. And finally, the key to getting 3 to 5 marks on a problem. Always show your work. Write the formula, show the substitution, and give the final answer with units. That's the recipe for full marks.
So there you have it. You now know exactly why your home is wired in parallel. But let me leave you with a final thought to chew on. Can you think of a device where a series circuit is actually the better choice? A situation where you would absolutely want the entire circuit to shut down if just one little part breaks? Think about safety systems. I'll leave that with you. Thanks so much for joining me.